Okay, so welcome to this lecture on heterocyclic chemistry. In this lecture, we'll be going through few reactions of furan and thiophene. When you compare the order of aromaticity of benzene with respect to these heterocycles, that is thiophene, pyrrole, and furan, the order of aromaticity is obviously first is benzene, the most aromatic compound, right? And next is thiophene, and then is your pyrrole, and the least aromatic of this lot is your furan. So why is this so? Why is the order of aromaticity in this order? In benzene, what happens is all the pi electrons are totally involved in forming the aromatic sextate. So in delocalization, all the pi electrons are involved in aromatic state. Now here, in the case of these three heterocycles, the heteroatom, which is more electronegative compared to carbon, these heteroatoms, they pull the electron cloud towards themselves. The heteroatoms pull the electron cloud to themselves. So which means there is uneven charge distribution. And more, one correlation that you can do is, more the electronegativity of the heteroatom, as you can see, more the electronegativity of these heteroatoms, less is the aromaticity of the compound. Okay. And this is also supported by your experimental calculations. If you look at the experimental values for resonance energy, okay, so benzene, I told you, is greater than thiophene, is greater than pyrrole, the aromaticity order, and is greater than furan. Now if you look at resonance energy, in terms of kilocalories per mole, okay, the value of benzene, of course, is highest. It is at 36. Then for thiophene it is 29, for pyrrole it is 21.2, and For furan it is 15.8. Okay, so what is resonance energy? Resonance energy is measure of extra stability of conjugated system. Compared to corresponding number of isolated double bonds. Okay, so this is experimental values, and of course for you should know that for pyridine it is 23 kilocalories per joule. So you can put it in order the aromaticity values. Okay, what is the consequence of this? Just take about furan. Furan is the least aromatic among this lot. So in terms of its reactivity, what might be the consequence? The first consequence of thiophene being least aromatic is that in places where electrophilic addition is possible, furan undergoes electrophilic addition. See, if it is aromatic, if it is most aromatic, it will only undergo what reaction? Substitution reactions. Okay. Now, because furan is less aromatic, it can afford to undergo addition reactions. So wherever there is prospect of forming stable bonds such as COO, single bonds in furan, so CO single bond by addition, where by addition reactions may be preferred to substitution reactions. Okay, wherever there is a prospect of forming, wherever there is forming stable bond, stable CO bond, single bonded CO. Now, one example we can quote here is furan. When you react it with bromine in other solvents, so what it will form? It will form tetra substituted bromofuran, right? Tetrabromofuran. Now, when you react it with a hydroxylic solvent such as methanol, the reaction, the product is quite different. Okay, so shall we go through that reaction? First, since there is bromine, bromination occurs as usual, must start in its usual way. So the lone pair this will fall back here. fall back, and this bromine, this will go and attack bromine. This bond leaves, it will to give you, and there is a oxonium ion that is formed here, uh, a triple bonded oxygen. Okay. Next, what happens is your methanol, the oxygen of methanol attacks this particular carbon, and bond falls back. Of course, there is this hydrogen that is there. So, to give you OMe. Okay. So, what will happen? Your this will be positive, and this deprotonation can occur, and to give you this addition product. Now, the bromine that was originally added, this bromine is pushed out by the furan oxygen atom to make a relatively stable oxonium ion. This, the lone pair on oxygen will kick out this bromine to form a stable oxonium ion. There is the first charge, and the second molecule of methanol will come here. There is a double bond here. No, 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 no. Something is wrong there, and mm, so, fine. Of course, there is a and deprotonation will occur here to give you an addition product. Okay. So this is your addition reaction happening on an aromatic molecule. Now, furan can also undergo ring opening reactions. A simple hydrolysis of enol ethers, phenol can give you 1,4 diketones. Let us look into that particular reaction. Ring opening reactions of furan. It's a furan, substituted furan. This on hydrolysis, in acid catalyzed hydrolysis, it will give you 1,4 diketones. Okay, so let us see the mechanism for this. I'm take a simple methyl substituted furan to make things easier for us. So the first step is, when you have a proton, the lone pair initiates the reaction. Now, since both 2 and 5, note here that the 2 and 5 positions are blocked by methyl groups, and therefore the attack happens at a third or fourth position. Very important. Wherever all the three heterocycles, pyrrole, furan, and thiophene, for a mono substitution, electrophilic substitution happens at 2 and 5th position. Only in cases where both of them are blocked. See here, both of them are mono substitution happens at 3rd and 4th. The reason is the number of resonance structures for the intermediate that is formed. More the resonance structures, stabler the intermediate. Fine. So next, a molecule of water attacks. And what you have here is see, next step is a little bit tricky. The OH bond falls back to give you C double bond O. This CO bond falls this side and the double bond attacks the proton. So to give you first, still an oxonium and of course water molecule can take away this proton. So what you have is 1,4 diketone. So a ring opening reaction of furan when you do acid hydrolysis gives you 1,4 diketone.